Hello again, everyone. Sorry for the delay and thank you for your patience. So we are back now. Unfortunately, two of the speakers were not able to present. That was the reason of the delay. I also wanted to let you know that while you're listening to the talks, you can write your question in the chat and we will ask your question to the speaker. So our first talk is CTBTO to manage earthquake short-term risks will be given by Farzad Azima.
Hi, I'm Farzad Azima, the product manager of Uling. Uling Ltd is a startup that is based in London and focused on detecting short-term seismic risks in 260 regions in 40 undercover countries. Short-term earthquake forecasting is almost reachable right now. We've developed many models generated to detect high-risk time windows when the probability of unusual seismic activity is detected. But still, some high-density regions in the world are unexplored because of data monopoly by seismological institutes, especially in preventing having access to required raw data. In 2015, we set up an earthquake early warning system based on smartphones. It could constantly monitor every change in the seismic behavior in the undercover regions. Some changes were recognized in some of the undercover regions before major earthquakes. We developed models to detect the pattern in 260 regions in 40 high-risk countries. As a main result, now we can say that short-term earthquake precursors can be detected utilizing the current technologies in most of the high-risk regions. During the efforts, we realized having access to some regions is abundant by research institutes like the International Institutes of Earthquake Engineering in Iran. CTBTO sensors can be very helpful to keep the research doors open, encountering data monopolies by entities like IIES. Especially when we know 15 million people in Iran and Tehran and Alborz province are vulnerable against the next historical and periodic devastating earthquakes in the regions. Constant data gathering, innovative algorithms, and models lead us to categorize current seismic situations at least into 3 low, medium, and high categories. One of the smartphones in the Uling seismic network recorded this data during a major earthquake in the northeast of Iran, a magnitude 5.7 earthquake with more than 400 casualties. Especially now that high-risk situations can be detected, a chain of reactions is helpful to prevent from being surprised by the next major events. Reactions that can be named Earthquake Preparedness Action Plan to manage risks, and even transit financial risk to the risk takers. Knowing the high-risk seismic time windows helps families preparing and defining roles if a major event occurred in exercise. Who transfer the financial risks, how to react during the earthquakes, how to find each other if the event was destructive, how to ask for help from families and friends are some of the examples that are related to the families. In most experiments and the undercover regions, high-risk time windows that followed by an earthquake were in 5 days. A few of them were in less than 10 days and fewer of them in less than 20 days for the specified regions. This diagram shows how CTBTO sensors help to keep integrated and decrease gaps in the data gathering stage. Raw data after processing is ready to use as input of NatCat models to monitor the undercover regions. We use a natural seismic index to categorize current seismic situations between low and high risk. A high-risk situation marks based on a threshold that is defined based on the last 5 years' average earthquake magnitude in the specified region. California and Nevada experienced 500th high-risk time window in 2021. It was 0.02 for the north of Italy and the north of Iran. To evaluate the accuracy of a short-term earthquake forecasting model, 4 parameters including true positive, true negative, false positive, and false negative needed to be analyzed. True positive for earthquakes have happened in the specified time window by the model, true negative which represents how accurate days with no risks are marked, false positive represents high-risk time windows that didn't experience an unusual event, and false negative that represents ratio or number of unusual events that are not detected and marked. In another aspect for evaluating the accuracy of the utilized model to detect short-term high-risk seismic time windows in California and Nevada, a region with about 10,000 earthquakes a year, but the true positive is 9/10, which means the models are not affected by the numerous earthquakes in the region to issue false positive reports, albeit the region is highly active. Of course, we didn't have an unusual earthquake during the experiment. As no unusual earthquake occurred in the region, we couldn't experience a situation like the last September 2020, in which our models successfully detected a high-risk time window for the region. The north of Italy has experienced 2 earthquakes greater than M4 between Jan and May 2021. Volcano detected 4 high-risk time windows in this period, which 2 of them followed by magnitude 4.3 and magnitude 4 earthquakes in the north of Italy and near Vienna, which was the first one in the last 5 years. 2 others followed by earthquakes near the capital of Croatia. Volcano successfully marked low-risk time windows that for this period it was 9/10 of the days. Volcano has 260 undercover regions in 40 high-risk countries. In this map, the dark blue colors represent countries that received accurate risk level change reports from hours until days in advance, and before at least one unusual seismic activity getting occurred. CTBTO sensors help the most encountering inhabitant regions prone to experiencing earthquake precursors and data monopolies that are created with some seismology institutes. Currently, models are accurate enough to start using to issue earthquake preparedness alerts, but the goal of using the data is very important to approve and decline the accuracy of the model. So the meaning of accuracy is different based on its case studies. It means while the accuracy of the current models is impressive to manage financial risks, but they still need more effort for an evacuation. At least the current models created new options to choose by residents and governments as a high-risk time window is detected. Are we close enough to short-term earthquake forecasting? We should say it depends on your case study. The answer is no if you are going to use the reports for an evacuation, as it can be a false positive report. On the other hand, the answer is yes, if you are going to transfer earthquake financial risks.
Okay, thank you, Farzad, for the presentation. No question. I do actually have a question for you, if you can still hear me.
Yes, I'm here.
Okay, maybe I missed that. What is the range of this short term you explained? So is it within days or month or weeks? I didn't get that.
We mentioned
Yeah.
we mentioned in the presentation it's most of the time it's less than 5 days. Okay? From a couple of hours until 5 days. A few times it was in less than 10 days, and fewer than it was 20 days. For instance, we have an example for the Iceland major earthquake in 2020 that we sent them an email to the IMO office of Iceland and informed them that we can see a high risk time window. About 2 weeks later, the largest earthquakes since 2008 hit the region. It's just one example. And about Italy, we issued an alert for north of Italy, and one of the greatest earthquakes, as we mentioned in the presentation, happened the day after. But most of the time it's less than 5 days, and of course it's really depend to the region. It can be very different region by region.
Okay, thank you. Then it's can be within few hours. That could be really for the early warning, not to evacuate the people, but to shut down like gas pipes or electricity within a large city. That could be useful if it's within few hours.
It's very accurate, not for for disaster management, but for risk management in the financial aspect. It means that shutting down gas pipelines, it is not still the case in this level of accuracy. But for instance, if you are going to transfer your financial risk to a risk taker, for instance, insurance company, it is the real solution that you can do it, because when such precursors are detected, most of the time you should expect an unusual earthquake, which means an event larger than the average of the event in the target region.
Okay, thank you very much. If we don't have further questions,
So, good afternoon. I just want to remind everybody that the chat is open for questions. So maybe if you have questions, feel free to pass them on to us through the chat, and then we will direct them back to the presenters.
okay, thanks. So let's move on to the next talk. It's the 2015 earthquake swarm of Fentale or Fentale volcano, multi-hazard threat for Ethiopians. Access to the coast will be given by Atali. I think it is also a pre-recorded video. So,
okay, my name is Atali. The title of my talk will be the 2015 earthquake swarm of Fentale volcano, multi-hazard threat for Ethiopia's access to the sea or to the coast. So to give you a background, the stress difference need to get extensional separation of two lithospheric blocks without what we see here. On the top panel is without, and the one the bottom panel here is with magmatic intrusion, according to back 2006. Again, as a background, we see here the African continent, as Craig et al. So when we go from Afar to the Okavango Delta along this African rift system in this direction, magmatism decreases, spreading rate decreases, earthquake depth increases, and also earthquake magnitude increases. So the best natural lab to study magmatic intrusion is the East African rift, especially the Red Sea, Gulf of Aden, and the Afar region here. So it's a dry land. It's very easy for most interested scientists to investigate around that area. But when we go to the Atlantic, for instance, according to James Abscope, you have to dive into the bottom of the ocean, which is logistically cumbersome. Here we see the power law distribution of earthquakes, volcanic eruptions. So our knowledge of size distributions also. So the one that we see on the left one is the Gutenberg and Richter power law distribution. So volcanism also obeys the same power law distribution, but the one you see here is, for instance, for more than 2 millions of years, geology, geochemistry, petrology, such kind of information, PAPL 2018. But volcanoseismology can give us a lot of information. For instance, here in Ethiopia, for the last couple of decades, a lot of magmatic activity has occurred, like the Dofan volcano, Amoisa Yellow volcano in 2000, and also Dabaho in 2005, which I'll talk a little bit more later. Here you see the Horn of Africa region, the Ethiopian rift here. This is the Afar and the Red Sea and the Gulf of Eden, and the red called beach balls. Fault plane solutions from naturally occurring earthquakes. So for the last couple of decades, as I said earlier, we witnessed a lot of magmatic intrusions. Like this one is the 2000 Gawani magmatic intrusion. This one is the famous September 2005 in the Bahu. That's the Aludalafila. And also Gulf of Eden 2010 and the Nabru 2011. So humans ordinarily don't notice them, but we are using seismology and also INSAR data. Here also from tomographic work of Hammond et al. 2013 and Ayala et al. 2017. If we superimpose the tomographic result at 75 kilometers light and seismicity of the region, it's really interesting much, and it's really questionable whether it's a coincidence or just a correlation, because this is where the low velocity anomaly is visible, the red ones, and that matches quite well with the seismicity distribution in that area. So one can ask the question, is magma seismicity in this region? Yeah, it's really interesting. Again, the one published in year 2015. In 2009, there was a peculiar activity in the Afar region. The one, the purple spot is almost the magmatic centers were activated in that same year, and which is really interesting whether the magma source is the same or just they happen to be just by accident in different places. This shows the station distribution in Ethiopia. Most of them are broadband stations and currently use helicopters almost on daily basis, real-time data acquisition that you see here, all these stations. The black ones are Ethiopian stations and the blue ones are neighboring stations. I mean, from other countries like Uganda, Djibouti, Kenya. So we use them for disaster management in this region. Classification of volcano seismology, you know, the volcano shows different features like what we see here, depending on the nature of the vapor. This the first one, for instance, is a high frequency or typical earthquake or mixed frequency event, and all the dynamism of the magma can be captured by seismic station, and it can be interpreted for volcano prediction purpose. And also the geography of long period earthquakes is also postulated to be, according to Woods et al. 2018, somewhere in this region, for instance, you know, this kind of long period signals, kind of resonance tube wave, and mostly they are captured by broadband stations, and tremors can also follow in that way. Sequence 5, there was a very huge magma intrusion in this part of the Afar Rift. That time there was not much logistics like stations, and but from available stations we managed to make something out of it, and it attracted a lot of international collaboration. And later on, very precise location both on the surface and also beneath the surface, a very nicely pinned earthquake hypocentral determination have been made as shown by Bellaccio et al. In 2011. So the main focus of just the Fentale activity in 2015, which is almost close to Ethiopia's access to the sea. There's the main road that goes from Addis Ababa to Djibouti, and it passes quite nearby. So this red cluster of dots were recorded in 2015 by our network. which is shown by the inset map in Ethiopia, right in this rectangle. So that's really the focus of my talk for today. When we zoom in a little bit further, this is the area. This is the famous Fentale volcano, but that activity was not right on top of the volcano. Instead, it was a little bit northeast of that. This one is just a sketch from Google Earth. Fentale is here. And there is Tilik Sabober and Tinis Sabober and Tinish Fentale is there. Beru, all these are volcanic cones in that region, just a kind of cartoon. So you can see Dofan volcano also over there, and the relative location of Fentale in the Ethiopian. Maps that I showed you earlier, the yellow, they're not yellow, actually it is green. That represents the swarm in 2015. And here we made also double difference location, and we can see migration of events from the northeast to the southeast direction, which might indicate the magma source, and also quite deep earthquake activity has occurred at that time. This one is also another technique to identify whether an earthquake has somehow influenced by magma or dike intrusion. The one on the left side is a hybrid earthquake, which means it has a very long period signal here and with significant energy down there. But this one is high frequency. And that one is just a long period earthquake, which is LP. And this is always an indication of tremor-like activity, which means that it came from a kind of magma region. So to conclude, the Fentale Dofan magmatic segment was shown to be more active than other volcanic centers in the northern Ethiopian rift by a temporarily deployed seismic experiment. Over 1,350 earthquakes are located, and the activity is clustered around Tinish Fentale, as I showed you earlier on the map. Northeast of Fentale proper with a maximum magnitude of 3.5 ml. There are VT or volcano-tectonic and also LP long period events showing that the activity is induced by magmatic intrusion. This intrusion seems to commence at the depths and migrate southwestward as it shallows to the center of the activity. Again, another also very important conclusion is that this is quite close to the main road access to the coast or the commercial route of Ethiopia. So if the activity was to continue and magma could flow, it could have blocked the road, and that may trigger a huge crisis for the Ethiopian society and the government as well. So this is, I think, the end of my talk, and thank you for your attention. I think this is all what I can say. If there is any question or comment, I'm happy to take. Thank you very much.
Thank you very much, Atali, for the presentation. If there is no question, I may have one question for you. On one slide, you showed Atali is offline. Okay. Apparently, something happened. He left the chat. Okay. So let's move on to the next talk. Will be, oh, that's interesting. The sound of melting glaciers in Greenland in a changing climate will be given by Laszlo. Laszlo, I think that would be live, so the floor is yours.
Thank you, Mr. Chairman, and I hope you can hear me, and I will share my screen so we can see the presentation too. So let me go to the full screen option. So I hope this presentation is clearly visible for you. Thanks again for giving me the opportunity to speak at this great conference. I've been to the science and technology conferences in the past, live of course, and that was always a very nice venue to meet colleagues and to discuss science. This time I would like to talk about recordings made by an infrasound array of the IMS, of the International Monitoring System in Greenland. This is a location which is quite unique. It's way above the polar circle in the northeast of, or the northwest of Greenland at 77 degrees north. On the left you see a global overview, and with Greenland as the great white spot over there. And then on the right there is a zoom in into this area where the array is located. It's called IS-18 for the treaty, or I-18DK from Denmark in the International Data Center. It's located near the village of Kanak. It's a microbarometer array, an infrasound array, so it is capable of measuring low frequency sound that we can't hear. It are frequencies lower than 20 Hertz, so lower than the lowest, the most deep sounds a human can hear. It's an 8-element array, so it consists of 8 microbarometers. And the advantage of using these arrays is twofold. First of all, with multiple sensors, you are able to estimate the direction where the infrasound is coming from. That's one important thing. Another important element is the fact that you can reduce the noise by measuring at more than one location. Especially wind has a negative effect on infrasound measurements. And by using multiple sensors rather than one sensor, you are able to reduce this effect of wind. The array has been operational for 18 years now. It started in 2004, and as you will see in the coming slides, we will focus on the summertime. These pictures are also from the summertime. The bay, as you can see, is open. There is no ice. There are some icebergs floating in summer. And in winter, this is a frozen area, and the array wouldn't be visible as it is on the left because it will be covered in snow. This is a fascinating picture, and I will enlarge it a bit because it has a lot of information in it. And I can talk about this graph probably for a couple of hours, but I assume, Mr. Chairman, that you won't allow me to have so much time. So I will try to be short, but let me dive into it. On the horizontal axis, you see a year, so from 2004 up to 2020. The figure ends January this year. So a total of 18 years of data is on the given on the horizontal axis. Then the vertical axis, there is written back azimuth. That is the direction of arrival of the signal, which I said earlier. Since we use multiple sensors, we are able to tell where the infrasonic waves, the sound waves, the inaudible sound waves are coming from. And then when it says 90 degrees, for example, then the sound is coming from the east. When it says 180 degrees, it's coming from the south, 240 the west, and 360 and 0 is from north. So you see, then you see a color it's either black and then it's raising to more lighter colors, reddish and white. Well, black means there are no events, and more bright colors means there are lots of events. So that is something to indicate to. So let me explain a bit then what you see. Each year you see a light vertical band. So that's a period each year where there are lots of events, infrasonic events, lots of sound waves are traveling over the array. And these vertical bands are always in summer. So in wintertime you see dark vertical bands, so then it's silent among the array. And in summer you see light bands, which means there is lots of infrasonic activity. When we go to the horizontal bands, then we see, for example, in the lower part of the frame, we see bright dots around, let's say, 20 degrees, so somewhat lower than the 30 degrees. And we also see more from the west, between 120 and 270 degrees, we see these light horizontal bands. Well, these indicate sources which are located at a specific angle with respect to the array. So, for example, each summer around this 20 degrees, you see a bright spot. So each summer there is a source active to the north of the array. We also see multiple sources to the west and to the south of the array. To the left, you see a histogram, and this histogram is just a simple addition. So we add the number of events which we see over the years. So we see an enormous peak, which I labeled 1 for the source to the north of the array. But we also see peaks 2, 3, 4, and 5, I labeled them, which are the sources more to the south of the array. And those are active each summer. Some summers the spots are brighter, some summers they are less clear, so we see variations in activity of this specific source each winter. Then to the top there is another histogram, and that histogram is a sum over the number of events in the vertical. So you see each summer you see many events, you see peaks in this histogram. Some summers are quite silent, so there are not so much infrasonic events, but when you, for example, look at 2012, you see an enormous amount of events, but also the last year, especially 2019, but also 2020, there are many events during summer which are being measured. And to make the figure even more complex or complete, that would be somewhat more positive to say, there is a red line, and that's a cumulative sum of the number of events. So we just sum the number of events each year. So you see a horizontal line in winter because there are hardly any events, and then each summer the number of events increases. And there you indeed see, for example, a year as 2012, but also 2019 and 2020, that there are many events. So let's zoom into these specific sources which we see here. I put them on a map. So you see I-18DK, that is the infrasound array near Kanak with a triangle. And then I plotted the directions of arrival, which we found in the previous slide on this geographical map. And you see to the north of the array, that's only a small arrow pointing in the direction of 1. There is a glacier, the Kanak Glacier, close to the array. On the other hand, when you look at 2, 3, and 4, they are opposite of the bay, and these are glaciers running into the ocean. The direction is pointing to these glaciers. And number 5, which I won't discuss in this presentation, is the island, which is also in the bay where we see lots of activity from. So let me now zoom into first is Glacier 1, which is what we call a land terminating glacier. The glacier ends on land, and later on in the presentation I will zoom into Glacier 2, 3, and 4, which are sea terminating glaciers as they are called. This is the activity of this source 1, the Kanak Glacier to the north, the bright spot which we saw in the previous slide. And in black is again the cumulative number of events. So each year there are events and we just keep adding them every year. And you see what we already saw a bit in the previous slide, that for example in 2012, but also a bit in 2011, there is a huge increase in the number of events. But it should also be clear from this figure that 2019 was the infrasonically the most active year we have ever seen from this glacier. So these are sounds coming from the glacier, and this is just a way of representing them by counting the number of events. Then you see a gray dashed line in this figure, and this gray dashed line is a line if the increase would be linear. So each year there would be the same increase in the number of events. Well, this is not true, and you see also a curved gray line, and this is the true fit to the number of events. So what we see over time is that there is an increase in the number of events coming from this glacier. We also have, and that's in red, actual measurements of the glacier, which is done by Japanese colleagues. They measured during 3 summers the discharge, so the amount of material, water for example, running off the glacier. And it nicely coincides, I would say, with a number of infrasonic events. So the infrasonic events and the discharge, so the amount of material running off the glacier, are in some way linked. So let's have a closer look then at the glacier itself. So I-18DK is in this figure again, that is the infrasound array, and the Kanak Glacier is there. And we are going, or the Japanese colleagues, walked down from the top of the glacier to the bottom, and doing these discharge measurements. And I think there we get a visualization by looking at the pictures on the next slides of what's making the noise. So why is that glacier making noise? There is nothing breaking off the glacier, or there are no pieces falling off of the tongue. It's just slowly melting. And well, this is the top of the glacier. So we have now also a look across the bay to these other glaciers, the sea terminating glaciers, which I earlier talked about. And the top of the glacier, everything seems frozen, but as soon as they start walking down, the melting starts. And going down further, rivers or small rivers, streams of water are created on the glacier. And I think this runoff, these cavities which are being made, these pipes that are made in the glacier, that's the true source of the infrasound we are seeing. So the mass displacement within cavities and pipes is typically typically you create a resonator capable of making this kind of infrasound. And this is all the way down where the glacier runs into the ocean. I also have a small movie of it, so you can't hear the sound, but you should be able to see the runoff. So as you can see, there is truly material running off this glacier, and noise is being made. I look at the chairman to see how much time I have left. Maybe you can raise your hand, and something like 5 or 10 minutes, hopefully. Okay, I think I'm still fine. So what's the cause of this noise? Well, the cause of this noise is the running off of material off the glacier, and well, what physical parameter is driving that? And well, you can imagine that is temperature. So what I plotted here is over the years, and the 2016, which is written on the vertical axis, is wrong. It should be 2020. This is just the average number of events per year. So remember, it are thousands of events in total over all these years. We have measured over 200,000 events from this glacier. But you see in red the average over the years. So you see the glacier starts to be active in June, and it turns silent again halfway August, end of August. So that's the period that the glacier is making noise. Then in blue is the surface temperature. This comes from weather models. The surface temperature over these 17 summers, the average surface temperature. And you see a nice correlation between the surface temperature and the infrasonic events. So when the temperature increases, the number of events increases. And when it decreases, the number of events decreases, the temperature is also decreasing. So we kind of understand what we are listening to, and it's temperature driven. So short summary for this part of the presentation: the Kanak Glacier is a land terminating glacier. It's not calving. There are no pieces breaking off the end of the glacier. The infrasonic activity is driven by atmospheric temperature, and the infrasound is generated by the runoff and possibly the subglacial drainage system consisting of all kinds of pipes and cavities. Then to the opposite of on the opposite side of the bay, we had the three sea terminals.
Laszlo,
Yes.
you may have 2 more minutes to
2
conclude.
more minutes. Okay,
Yeah.
I will speed up because I'm way too enthusiastic of the first part, so I can be a little faster with the second part. We have 3 sea terminating glaciers. The activity, in a similar way as we did previously, is shown here. Overall, we see an increase in activity over time, although it's different for each glacier. And now the question came: what's driving these events? These are calving glaciers, so pieces are breaking off and falling into the sea as possible source of noise. But here we see temperature again, and the number of events. So the number of events in blue, and surface temperature in red. So what we see something different than the other glaciers. When the temperature is maximum, the surface temperature in red, then the number of events in blue is just starting. And when it reaches the maximum, the number of events, the temperature is already on the way back. On the other hand, we see the sea ice concentration. And when the sea ice concentration is minimum, then the number of events is maximum. And this shows that the activity is correlated with the sea surface temperature rather than the atmospheric temperature. So the calving of the glaciers is coupled to the temperature of the water. When the sea ice is minimum, the sea surface temperature is highest. So there is another correlation in this case than with the land terminating glacier. So to conclude, Mr. Chairman, hopefully in time, high resolution observations can be made of glacier dynamics with interseasonal and yearly variations being visible. And the great thing is, it's of course an array put there to verify the testbed treaty, but by just passively listening to the atmosphere around you, you can also get this information about glaciers. And we retrieved two different mechanisms. One, the runoff correlated to the atmospheric temperature, and the other one, the seawater temperature correlated to the calving of the glaciers. I thank you for your attention.
Thank you very much for the presentation. I do have a question for you. I saw that the two jumps in the cumulative plot you showed, one of the first few slides, at 2019 and 2020. So have you considered these two jumps with the average change of temperature, not locally, but in a much larger area, even globally? Have you considered that?
Yes, that will indeed be a good next step to make. I don't have a definite answer, a quantitative answer for you in that sense, but I think we know from other studies and observations that the last few summers in the Arctic have been very hot. So I can imagine that the high peaks in infrasonic activity and thus the high activity of the glaciers in terms of melting and calving is indeed well correlated with a global rise in temperature. But we have to quantify that.
Okay, there is one question on the chat. The speaker can see it, or should we? You should see.
I can see them actually.
Actually, you can see.
Yeah, you can see the
Yes.
question. Yeah.
Yeah,
Maybe it's good to repeat the question for everyone because not everyone is seeing the WebEx chat. So the question for everyone is, are the characteristics of the glacier coast signals sufficient for categorizing them automatically? I give the floor to you, of course, for the answer.
Yes, thank you. And that's a very interesting question. Yes and no. Yes, in terms of the fact that we know where they are coming from and when the specific source is active. So that will help a lot. We know something about the frequency content. They typically are present between 1 and 5 hertz. On the other hand, locally there are other noise sources in the same frequency band. So yes, it's possible on the basis of where the energy is coming from, the time it appears and the frequency content, but it will be a challenge to distinguish it from other noise sources too.
Okay. Thank you again. Let's move on to the last talk. It's the value of the open data from globally distributed geophysical instrumentation networks. Will be given by Robert. I think that's also a pre-recorded.
Oh, I'm Robert Woodward, and I'm with the Incorporated Research Institutions for Seismology. And I'm going to be talking today about the value of open data from globally distributed geophysical instrumentation networks, or really any long-term geophysical network. I'd like to acknowledge my co-author, Katrine Hafner, also from IRIS. IRIS operates a variety of networks, including the Global Seismographic Network, shown on the left. This is a network of about 150 long-term stations distributed globally and is operated with the sponsorship of the National Science Foundation and in partnership with the U.S. Geological Survey. This is a network of very high-quality stations, been operating for over 30 years. We have also operated a variety of other networks, such as shown on the right. This is part of the EarthScope program the US Array Transportable Array Network, which deployed hundreds of stations across the continental United States, as well as more recently across Alaska and parts of Western Canada, generating upwards of 10 years of continuous data. So the point I'd like to make today and in the subsequent slides is that open networks that are providing long, continuous, and consistent observations can serve operational missions, fuel discovery, capacity. And I'd like to talk about some of the important elements of such long-term open networks. First, a network must have comprehensive metadata. The screenshots shown on the slide are from the metadata aggregator that we operate at IRIS. And so these particular screenshots show the metadata for the station ANMO in Albuquerque, New Mexico. And they show every configuration of this station going back to its origins in 1989. Every sensor that's been installed, the orientation of the sensors, the sensitivity of the sensors, every channel that's been logged at this station is documented in the metadata. The metadata are made openly available so anybody can use these data and use them accurately with this kind of metadata. And so really, to maximize the use and value of data from any network, and especially long-term networks, requires consistent and well-documented configurations, such as are shown here. Another important factor is open sharing of quality results. The graphics that I'm showing on the screen now are computed for the IRIS Data Management Center holdings. These metrics were computed by a program we call Mustang, computes a variety of metric data in our archive, and then we openly distribute these quality control metrics. Further, we share the algorithms that we use to generate these metrics, and in some cases, we've even provided code, open source code, that allows others to run the same metrics on their data on their computer. The importance of quality control like this is that these metrics allow network operators to detect problems and improve the performance of their stations. It lets scientists that are using the data make determinations about the quality of the data, which data they should use, which data they shouldn't. But it also lets us establish norms and standards for network operation. What are acceptable noise levels? What are minimum noise levels, maximum noise levels, and similar considerations for all facets of the data that are being collected. So shared quality control results help promote best practices in network operation. At our stations, we also operate suites of sensors. Once you've of establishing a network location where you have power, you have permits, you have communication, and so forth, it may be possible to install other sensors. For example, at many of our sites, we have very broadband sensors in whether they're installed in post holes or boreholes or in vaults. Sometimes higher frequency sensors that can go up to 100 or 200 hertz, strong motion sensors, which will stay on scale even in the presence of meteorological sensors recording channels such as temperature, humidity, wind speed, barometric pressure, and also infrasound sensors. The value of having a suite of sensors at a site is it lets us understand the signals we're seeing. So various phenomena might be recorded on more than one sensor, and having the multiple recordings on different sensors lets us untangle what the source of a signal is. Some cases it lets us correct the noise we see on one channel that's due to various factors, and we may be able to do that because we have multiple sensors recording. So really, multiple sensors open up new observational capabilities and let us understand the data even better. Have long-term, high-quality, open stations variety of expected and unexpected discoveries. For example, with the Global Seismographic Network, we expected the data from this network to be useful for studying the lower mantle. So I show an example in the upper left of the screen of a recent study of lower mantle structure. Now, the high quality of the data and the accurate metadata allow new techniques to be used and really allow the data to be pressed to its limits in terms of extracting signals and making discoveries. But when the GSN was deployed, what wasn't expected was that the stations would be used, for example, to study the temperature of the world's oceans and the variation of that temperature with time. And so this is really an example of deploying networks, operating them consistently, and making unexpected discoveries. Finally, I'd like to draw your attention to the images on the right-hand side of the screen and just note that open continuous data enable a wide range of observations of transient, seasonal, and other events. And data from the networks that we operate have been used to study all the phenomena that are illustrated in the graphics on the right. And the key is sharing the data openly and the other factors that I've been describing. I'd like to make the case that open data, open networks are really a world resource. At IRIS, at the data management center that we operate, we distribute data to individuals and organizations around the world. The pie chart on the left side of the screen shows our usage statistics just for the year 2020, in which we distributed data to individuals in over 200 countries. But really, people worldwide are using data. The quantity of data that we distribute is shown on the left. The bar graph, each bar shows a year of data distribution. And in 2021, we're already projecting to distribute over a petabyte of data. And this is many times the rate at which we ingest data. The data are being used in long segments, short segments. They're being used from global networks, regional networks, and they're being used for a variety of purposes. So the case I'd like to make here is that worldwide capability is enhanced by more people in more countries using more data. This is really a form of capacity building, which is the focus of my next slide here. Open networks build technical capacity in multiple ways. Of course, they build capacity through access to the data, that's obvious. But there's also access to designs and standards. For example, when we built the transportable array in the continental US, after we finished, we published the report shown on the right. It's openly available, and it documents every facet of the design, construction, installation, and operation of this network. So we can share this information for the benefit of all. Access to QC techniques and tools, of course, builds capacity and improves everybody's ability to operate their networks to the highest standard. Networks that are open and share their results drive vendor developments. Vendors can develop new equipment. We can get this deployed into the field to the benefit of everybody as new breakthroughs in technology are developed. And finally, by sharing data openly and sharing the results from different networks, we can support everyone's operational missions and drive discovery. It builds everyone's capacity. So in summary, open data, open networks, open standards, open designs provide numerous benefits. Some of these benefits are an improvement to every network's ability to meet its mission and its operational objectives. It enhances research and discovery, and that in turn enhances the ability of network operators to meet their mission and operational requirements through improved algorithms, improved processing techniques, and improved quality. And finally, open data and open networks build a broader base of scientific capability worldwide to address societal needs, such as nuclear monitoring, the subject of this conference, but natural hazards, applications in the energy sector, and more. So I'd like to leave you with this thought. Open networks lead to the identification of best practices. which in turn allows all networks to increase their value and their performance to the benefit of all. Thank you very much.
Thank you very much for the presentation. There is no question. There is no question in the chats. Yeah. I'd like to add something to your talk, Robert, because recently there was a lot of discussion to when people use the open data. Of course, they mentioned that in the text and they thanked them in the acknowledgement, but recently there has been a DOI number for each network, which people can really cite and refer to the database or data center that they use. In this way, I think we can thank all of the effort done by the people in the data center.
Yep, I agree with that. I think it's really important in the development of the digital object identifiers, or DOI numbers, as you mentioned, is really a great development. And I think it's important for a lot of network operators to be able to show their funding agencies that their networks and their data are being used. And so the citation of the data in publications and when the data are used is an important part of being able to identify and essentially count the utilization of the data. And that's an important part of maintaining support for networks. I think it's a great development.
Okay, thank you. We have a question for you, Robert. The question is, do you see the open data going into the cloud for storage?
Yeah, I think that's definitely a trend. Certainly we're working on that at IRIS, and I know other data centers are as well. Moving from hardware and storage systems that we operate to hardware and storage systems that are operated by various entities just kind of in the cloud. In our own case, it is requiring that we rework some of the software and underlying databases to make the formatting of the data more optimal for storage in the cloud. And then I think that there are a lot of benefits that will come from that in terms of being able to provide very high-speed access to a lot of people. In some cases, also having the data being very close to very high performance computing resources, so that in some cases it might be possible for people to do large computations with the data without ever even downloading it from the cloud. I think the challenges, though, certainly that we're seeing are which cloud providers will we use? Will there be cloud providers that sort of specialize in supporting scientific data, or will we, with our scientific data, be out there in the commercial marketplace procuring cloud services and having to compete with other commercial activities, and potentially worried about what the costs are?
Thank you. Okay, you can go ahead.
Okay, there is another question from Laszlo in the chat, and the question is, how hard or easy is it to handle changes in metadata over time? The floor is yours, Robert, to answer that question.
Oh, okay, sorry, I wasn't sure if that was directed. Oh, it was from Laszlo. So tracking metadata with time can be quite challenging. Not only do you need a system, for example, many organizations worldwide are using the SEED format, the SEED standard for exchanging seismic data as a way of documenting metadata. But over time, the metadata has become richer. There are more sensor types requiring new fields in the metadata, which has required us to move in new directions in terms of how we describe and store the metadata. And I think that the real challenge is continuing to propagate kind of international standards so that we're all describing our instruments in the same way and understanding the definitions of key metadata fields. And I think that this international collaboration to set and maintain these standards is just absolutely critical so that we can exchange the data and know what the metadata means. Yeah, it's a good question. It's a really important topic.
Thank you very much. I think there is no further questions. We can now conclude the session. I wanted to point out that you can reach later to the presentations. If you have further question, you can send a message to the speaker directly on the webpage or on the mobile app of the SNT. And I also would like to thank all the speakers for the very interesting talk. And we'll see you all in the next SNT in 2 years, hopefully in person.
Yes.